Hello and welcome in this early hour. I appreciate you all coming for faster, better design. My name is Dmytro. I'm going to be here with you. I don't know if just 3 of you or 300, because these lights are really blinding. So apologies if I'm not looking at you straight away, because I just don't see anything. So with that out of the way, let's get started. What I'm going to cover today is talk about low latency. I want to define what low latency is, and I want to talk about design principles, because when we design things for low latency, we need some guidance. Because typically, when you solve a problem, there will be conflicting concerns, and you need guidance to help you solve it. So that's where design principles come in, and they are rated in the most important to least important, based on experience I've got in Aeron. They're similar to what Aeron has, not exactly, they're more generic, but if there is a conflict in the problem solving, you basically choose the one with top priority over the one with lower priority. That's how it helps you guide it. And at the end, we're going to look at what Aeron is and what it can do. But before we do that, first a disclaimer. In preparation of this talk, no LLMs or Gen AI was used. So if there are any hallucinations, they are all my own. And I'm very proud of it. Let's get going. So let's first define what latency is. So latency is the time it takes from a stimuli to get a response. For example, you click on a page, and the page is loaded and fully painted in your browser, or you are talking in your microservice architecture world to another service, you send a message, and you receive response. So this is the form of latency I'm going to refer to. But what is low latency, and how low is actually low? If you can imagine a time scale, on your left-hand side is seconds, on the right-hand side is nanoseconds. We could put different types of software on that scale. So in second world, you think about things like batch processing that run overnight, maybe hours even. Back office applications when somebody clicks on the screen, waits for something, and does. If you go to millisecond scale, you are in a world of gaming, right? So your typical game needs to do at least 60 FPS a second, which means a 16 millisecond per frame of processing that the game needs to adhere to. It can also be human trading. Look in the screen, things go up, and they just press buy, sell, whatnot. In the microsecond scale, so every time we shift to the right, or we divide by 1,000, right? So we kind of go from millisecond to microsecond, so 1 millionth of a second. You are looking into like high-frequency trading world. Surprise, surprise, most of the customers that Aeron has or use Aeron library, they're in that world. But things like soft real-time systems where you don't have a hard guarantee of something event happening, but you want it to happen consistently at like microsecond scale. And then to the right-hand side, you have things like hard real-time systems, military applications where things cannot happen. They have to happen in a discrete amount of time. Or you have ultra HFT, as I used to call them. They're people trading, not in software, but in hardware. You have things like FPGAs. You have custom ASIC, where literally people's programs are being manufactured for them on a piece of silicon and then installed into the switch. So there is no conventional computers anymore. It's all happening basically at the end of the network cable. We're not going to talk about this. We're going to talk about microseconds. And what is possible, how we can do this in the world of Java. So hence design principles. The first one is no garbage. What does it mean, no garbage? You probably guessed it has to do something with allocation. And why don't we want to allocate? Like typical Java programs and the APIs designed around Java is allocating everything, because like it's easy, allocate, forget. Garbage collectors are good, allocations are cheap, you have thread local allocation buffers and other tricks that JVM is doing to you. However, you need to collect the garbage, so garbage collection is not free. You need to compact your heap, which gets fragmented over time. You need to do extra work, and typically your application will be paused for that. Those pauses are typically on a different scale, like millisecond scale, and if you write microsecond level software, you cannot achieve your goals if your application pauses for milliseconds. And another one important reason is allocation, however cheap it is, however it is implemented, is basically a guaranteed cache miss. And a cache miss on a modern CPU means basically you're stalling and you're waiting for a couple hundred cycles for things. And this is infinity in the world of CPU time, so you're kind of wasting a lot. All right, so to drive some example, let's say I have this very stupid JSON kind of like structure here with a key and a value. The key is 64-bit integer, the value is 32-bit integer. And I want to process it, and we'll look in a couple of examples how we want to do it. So let's say we're on JDK 8 still. There are some people there. Don't be shy, don't be embarrassed, it's okay. You're all in a safe place. And so what I want to do, I want to collect, so I'm receiving those over the network, right? So I have an IO byte buffer here that I'm receiving the packets from. I know there is a JSON inside it. And then I need to parse a key and the value and then accumulate. So we have a hash map from long to long where my keys are obviously keys, and the value in the map is a sum of all the observations I received. So it's tiny, silly program. If you look closer, though, there are some allocations here. So JSON substring, there is a JSON here, there is a byte array that we need to allocate to get the packet, right? Okay, can we do better? Let's say we go to 21 and try to use all the force of 21. Well, that wasn't a big difference, right? The only thing that changed is that we have now parse long or parse int at an index. So it only took 22 years to add it in JDK 9 for us to be able not to get a substring to parse something, but actually to go and say, within this string-like thing, I want to parse a certain offset. Great. And that works with char sequence, unlike the other parse method. So it's all nice. What alternatives? Well, what if we use a library called Aeron? That's what Aeron is using. I'll talk about it at the end. But so it's a little library. It has some interesting utilities in it. And everything you see here looks totally different from what you might see in JDK world because it has dedicated collections for things. For example, it has a concept of a buffer. It's called here an unsafe buffer. It can wrap any type of buffer, right? And it can wrap it means it's a flyweight, right? So you create it once, you don't allocate, and then when you received your, let's say, packet, you just wrap byte buffer, you say give it offset and length, and then you point basically where the packet is. You go on from there, and you want to parse a value. So in the Java world, you need a string. Well, in a Aeron world, we know that we're working with binary, so why would we go to string? Why can't we parse things out of binary? And so the buffer, the unsafe buffer here, it's called direct buffer actually as an interface, gives you methods such as parse long, parse int, and so on. And typically, a buffer will have binary data to extract from. You don't have to parse anything, but this is just an example that if the data was text, you can parse it directly. And it has dedicated collections, which are primitive-based, right? So you don't allocate on keys and such. And this is a special kind of map. It's called counter map. So it has even nicer API where you don't have to get and put and whatnot. You just get an add, and it does the counting. All right, so with all the talking, why it matters. So if we look at the execution time on it, this is running, by the way, in JDK 21. So although it says JDK 8 to JDK 21, it's just the API part. The actual execution was JDK 21.07, the latest release. And what you see that the execution time of Aeron, it's 3 to 4 times faster than everything we've seen on JDK world. Well, why is that? Well, obviously, it does not allocate, as I mentioned. So you have 0 allocation in a Aeron case, and both JDK versions allocate at more than a gigabyte a second. There's a bit difference in how many bytes, but if you look closer to that, if you look at the like Linux perf level for that, you'll see that well, Aeron is doing more instructions per cycle. IPC is higher. It means it uses CPU more efficiently. It has less L1 cache misses. Obviously, it doesn't allocate. It doesn't need to stretch cache or pollute stuff in the cache as well. It does less load, less everything. Instruction count is lower. Everything is lower. And across onto JDK world, you see the cost of those allocations and indirections kind of biting us. So what does it teach us? Well, if you want to design something for low latency or any decent performance in mind, you should not think about allocation as something that you get for free. But you should be cautious about that. It's okay to allocate in certain paths, but not probably in the hot paths of your application. So how you go about this? Well, it starts kind of from the outside in. If your interfaces to the system use JSON or XML or anything like that, you're already screwed. So think about encoding data differently, prefer binary. There are good libraries out there like SBE, CAP, and Protoflat buffers. There are also bad binary protocols out there, so think about that as well. Using flyby pattern. Instead of allocating, keep on reusing existing objects, just map them around things, and use the APIs that don't allocate. Think about things like primitive collections, right? You have in JDK primitive arrays, you have things like Aeron, Eclipse collection, FastUtil, and other places to give you that capability. Unfortunately, we don't get them in Java. Maybe with Valhalla, it's magically everything will start working. We don't know yet. But so the next design principle is called natural batching. Why are we talking about batching at all? Well, think about a thing like you have a service, downstream service, and you're sending individual writes from it. That each writes cost some X amount of time. So if you have to send 10 things, you're just wasted 10x time because you're wasting time, let's say, preparing a network packet or something. That's always their fixed cost. What batching helps you to do, batching helps you to amortize that cost, right? So instead of sending one thing at a time, you send like 5 things at a time. So instead of having 10 individual writes, you're doing like 2 batches of 5 writes. And we'll see the effects of them of that later, but that's kind of that's surprisingly powerful technique, and some people think that might, for example, affect latency bad because you're going to wait for a batch. So we're going to see that that's not the case. So how do you do what's called here natural batching? That thing just suggested you wait for batches. Well, that would be bad if you sit there and wait. A much better design, though, is to separate right into your resource to another thread. So think about it. You have a thread that needs to write, let's say, to a network or something. I call it here sender thread. And it, instead of writing directly to the network, it sets it into the ring buffer or a queue of some sort. And then another thread, a batching thread, going to pick it up. So what you've just done, you've decoupled the two. And not only that, but you also protect it against like overloading resource and do other things. And it allows batching thread to pick up as much data as is there and send in one batch. So batching thread is not sitting there, just wait. Well, it kind of sits there and waiting, but your sender threads and everything needs to write to the resource are no longer blocking. They basically just offer to the hopefully like lock-free ring buffer that you have, and the other side picks it up and sends stuff over. All right, threads are evil. We are living in a multi-core world. This thing has, I don't know, 16 cores, 32 cores. Don't no longer remember. Your phones have lots of cores, and so we should use threads. Well, we should consider not use threads. That's what I'm saying when I mean by threads are evil. This is a paper from 2015, scalability, but at what cost? And what they've done, they looked into a couple of data parallel systems and came up with the mnemonic cost, or its kind of configuration that outperforms a single thread. So what they've done, for every problem they were trying to solve with things like Spark and Hadoop clusters and whatnot, they wrote a single-threaded application that does exactly the same, and then compared the efficiency. And what they found? Well, they found that in all surveyed systems, the cost is very large, typically in hundreds of cores, and sometimes never beaten single-threaded programs. So you can throw 1,000 cores at the problem, and it's still slower than a single-threaded application. Well, when I was preparing this talk last year, it occurred to me that smells like embarrassingly serial problem, or the problem that you should be embarrassed if you write a parallel solution for, if you can write an equivalent single-threaded design. There was another blog post from 2014, I believe. Don't recall the name of the author, but it was about 235 times faster than Hadoop cluster. And so the guy basically threw a bash script with a couple of Unix utilities to solve exactly the same problem that Hadoop cluster is solving, and got to 100x performance results. Again, all single-threaded, all just pipelining things between different utilities. So you don't always need threads, but sometimes you do. So what's the approach here? Well, if you can write things in a single thread, use single thread. There is no reason to go parallel and, especially stream.parallel or whatever, just stop. What are good uses of threads? So one design approach is to use like processing pipeline. If you know, in modern processors, you have like a pipeline of execution. You first decode the instructions, then you parse them, then you execute them, then you retire them. And so you have a pipeline. And each part of the pipeline can be a thread in the application, which does exactly one job. So it doesn't switch between different things. It's not like a common fork pull. It's just, and you just pass things between stages of the pipeline. The caveat here is that you need a good queue or ring buffer to go with it. So look for one. Aeron has some log-free ones that kind of allows you to cheaply pass jobs between those states. Or background and helper threads. Amazing. When you want to offload something from your hot pass, let's say login or lookup or whatnot, you can do that with the helper threads. But just don't sprinkle parallel on everything you do. That's not going to scale. It's going to be bad. No exceptions. So what does no exceptions mean? No exceptions is not about throwing exceptions or anything like that. It's about the focus of your main algorithm. So if you are processing something, parsing something, sending something, and you know there is a like 99% of the time there's a particular message type or whatever, do that first. So your main pass, your main message pass, your main processing pass should correspond to dealing with the main thing and not dealing with, oh, what if your user passed null? What if this? What if that? Where you have all this setup, you have all this stuff that just clutters it, and it introduces branches and other stuff into the hot pass that you don't need. And it's okay to take exceptional cost for exceptional cases. If user did pass a null, it's okay if it takes X amount of time, because that's not the main part of a message flow. Here's an example. It's probably hard to read. There's a lot of code here, but that's from the guts of Aeron. In Aeron, when you poll for messages, you have to supply a thing called fragment handler. The messages might be fragmented, so you typically wrap your fragment handler in this thing called fragment assembler. So fragment assembler has to deal with the fact that some messages come as fragments, needs to assemble them. Assemble means copying memory, stitching stuff together until you have a full message. Well, what Aeron does here is that it first checks for messages unfragmented. If it's unfragmented, you can directly process it. So the first if statement says, if it's unfragmented, straight through to the user code that invoke that, no extra work. If it's fragmented, it calls to a separate method, because we don't want to clutter this one. We want to have this one nicely JIT optimized. And if the else block becomes frequent enough, it's going to be JIT compiled and inlined and all that stuff. But until then, if all of your messages are unfragmented, you don't want to take that exceptional cost. And for example, JIT will even remove the else block completely for you and kind of leave you with just straight through delegation. Single writer principle. So if you are writing to a shared resource, I had this example previously where it is network, database, anything like that, and you have multiple threads competing, what happens? Well, that resource becomes contented. Contention means queues are formed. It also means that in order to protect your precious resource from dying, you need to deal with concurrency, right? You put big fat locks and semaphores around it. You introduce crazy concurrency protocols. They're probably buggy, they're not working, and this is just not the right way to do. So what is the alternative? Well, you've seen kind of glimpse of this previously. What if you separate the two? So you have a single writer thread that can write to your resource, uncontended, single threaded, easy to test, easy to write, no problem there. And you just say that all the sender threads, they communicate with a ring buffer. Again, if you get data structure from somewhere else that is well tested and hopefully log-free or invade-free, you're in good spot. There is no location, everything goes through the ring buffer, and writer thread can pick it up. Moreover, writer thread can do natural batching, because it can just concatenate all the things that all the threads done and ship them into one in one request. So you kind of win-win on two sides here. All right, that's all good. What else do we have? Well, sharing. So I talked about that you should not use threads and everything. And so if you do use threads, then there is a question about shared state. It's even worse if it's shared mutable state, because that's just a recipe for disaster. So don't share state. So it's much better to have state localized to a threads. And it's a natural fact if you, for example, do things like pipelining, right? If you have different stages of your application, like receiving data, enhancing data, sending to external service, and if each of these compartments is done in different threads, they're naturally different. There is no shared data, because one receives like raw packet, does something to it, send it to another stage, which does something to it, send it to another stage. So you have natural message pass in between, and communicate by message passing is much better than having a global shared state that is mutated. So try to keep data local to a thread. It's going to be hot in the cache. It's not going to pollute things, and it's going to be nice to the underlying CPU. Good. What else we have? Well, we have a thing about copy. So copy is interesting. If you look at, let's say, a message pass to a network, and you use, I don't know, Java sockets or whatnot, so what you have underlying model underneath of that, let's say on Linux, on BSD systems, called BSD socket. So you do something on the user side, you fill up your packet, you set it through a socket. It has to be copied from user side to kernel data structures, usually more than once. And then eventually it needs to be copied to the network. So there's lots of copies everywhere. And copies are bad, because you're just basically wasting CPU cycles. They are relatively cheap to execute, but you are typically copy means you're allocating something, so you're taking a cache miss and you're doing stuff like that. So how would you go about not doing copy? Well, again, it boils down to API design. Can you avoid copies? It doesn't. This is like a very, very low level design principle, so it's not a top level concern like allocations themselves. But if you can avoid copies, do that. Here's one example that we have in Aeron, sorry. There is two ways to send a message in Aeron. So you have an abstraction called publication. You can offer your binary encoded message as like a buffer, which means Aeron has to copy from your buffer into the underlying log buffer data structure. Or you can claim the space in the buffer. And so you're basically doing zero copy. So Aeron allows you to do that. It's not free, because there are certain limitations to that API. For example, you cannot try and claim more than MTU worth of data, because the underlying things then go on the network, for example, and you're constrained with that. So you can use it to like send in small messages and such, so it kind of gives you that last mile. As I said, it's not the most relative and important concern here. But yeah, keep in mind that copies are not cheap, and if you have ways to avoid extra copies, redundant copies, it would be good. Sometimes it's a trade-off, right? If you have two different threads and they need to process something, you might think, oh, I don't want to copy, therefore I'm going to share this mutable state across different threads. That's bad. So in that case, copies is a good thing to do. You give every thread a different version to work on. All right. So I mentioned kind of bulk of this is coming from Aeron. So what Aeron is? Aeron is a project that started in 2014 by these two gentlemen, two absolute legends in our field, Martin Thompson, Todd Montgomery. If you haven't heard about either of them, Google them. You'll be surprised. Martin Thompson of Mechanical Sympathy and Disruptor fame, and Todd, been around the corner a while with lots of messaging products and ex-NASA researcher. Amazing people. So they started in 2014. Martin got approached by a company that said, they wanted him to write a messaging system with one particular requirement, or actually two. One was low and predictable latency, and another one was it has to support fan-out, so it has to send data across to multiple destinations. So they started writing Aeron. So what Aeron is? Aeron under the hood has three main things to it. There is Aeron Transport. That's the messaging part. That's where it all started. There is also Aeron Archive, and there's Aeron Cluster. So what is Aeron Transport and why it's unique in the way it was built? Well, I mentioned the requirements, right, that was there. So low and predictable latency and high throughput. Surprise, surprise, those are not conflicting. Well, they are, and most of the literature out there will tell you that you cannot have low latency or high throughput. Choose one of them. Well, actually, if you design things properly, it's not surprised that you can do both low latency and high throughput simultaneously. It's a brokerless transport, so you don't have a middleware or anything installed. You send in messages from endpoints directly to each other. It's a reliable transport, which means if there is a data loss, it will be detected and repaired. And it's built on top of UDP, so it's OSI level 4 protocol. It presents itself to the network as UDP packets with additional headers on it. And it supports everything that UDP supports. So you have unicast, that is point-to-point calls. You have multicast. That was the killer feature why they chose to do UDP, for example, not TCP, because multicast. Because the network you send a single packet and then it's distributed to hundreds of devices on your network by the network itself. So you don't do any extra copies. And it has another unique feature called multi-destination cast that is simulated multicast. In environments which don't have multicast, Aeron will do multicast for you. For example, cloud. It also does IPC. So if your processes happen to be in the same box, you can use Aeron for very efficient IPC, like we're talking 100 million messages a second, what it can do. It has, from get-go, built-in flow and congestion control. So flow control concerns itself with being able to protect subscriber from a fast publisher, and congestion control is about protecting network from a fast publisher. Interestingly enough, in Aeron case, the flow control also covers IPC, and that's something that other systems don't do. If you look a bit under the hood, we see some of the design principles that we talked about previously in play here. So we have here a split. So Aeron is split into the client and the media driver. So at the transport level, you have a client that is separate from the media driver. You can have typically one media driver per box and lots of clients using it. The media driver underneath it uses pipelining. So there is a sender, conductor, and receiver through separate threads, although you can configure it to run on a single core. But typically, there will be 3 different components doing 3 different things. So sender is concerned from taking your data, shipping it over the network. Receiver does the opposite. It listens on the socket, picks out the data, gives it back to the application. And there is a conductor thread that orchestrates the two and manages resources, like creation of publishers, subscribers, and other things. And among other things, it does things like log buffer cleans up and other activities that it offloads from the application or send and receiver threads. There is another interesting bit here that there's a photo console. This container-like thing here is a log buffer. That's the wait-free data structure that underpins Aeron. It's unique in its design. It has a very interesting approach. Each log buffer consists of 3 parts that are cycled through. It's not a single file that keeps on growing. If you want to know more, Martin did a great talk in 2014 about design of Aeron, why it was designed this way, and he goes in much more detail about how the data structure works, what happens under the hood, and other things. And here, what's worth also pointing is that we talked about things like single writer principle, natural batching, stuff like that. They also come into play here. For instance, the sender, right? So sender is the one sending the network. It's a single writer to the network. There might be multiple publishers, there might be multiple publications in the system. Sender will just cycle through them all, pick up as much data as available actually that fits in network MTU, and ship all in natural batches over the network. The same the receiver side is the only one listens to the sockets, it picks it up, it then distributes to the application. There's also interesting place of 0 copies in here. For example, on the receiver end, you see it says subscriber. What if you have multiple subscribers to the same stream? Well, typically, if you're using different messaging products, what you're going to get is that each subscriber has its own copy of the data, which means either it has to subscribe to data separately, so it opens its own socket and listens to all that, so you actually receive packets multiple times, or if it's a single socket, after receiving, each subscriber has its own copy. Well, Aeron doesn't do that. Aeron gives you 0 copy under the hood. So what Aeron does instead, it builds that log buffer data structure here, and then it's shared across multiple subscribers. They have basically pointers to the same thing at the same time, and it handles things like flow control and making sure they don't step on each other, that the slow ones will slow down the publisher, and all the good stuff that I mentioned previously about flow control. but it does all the tricks under the hood. All right, that was the transport. So what does the archive do? So archive takes the transport and adds persistence to it. Because sometimes you don't want just to send data from A to B. You want to ensure that your data is not lost. So you want to record data as you send. That's called here live recording. And once you have data recorded, you can replay it. So imagine you have a slow subscriber somewhere that cannot keep up with the rate of data. Well, you can record the data to the archive and get that processed. Or you want to process historical data. You sent something a week ago, and now you want to find out what it was. Or maybe you have like an audit requirements. You need to persist the data. So data is there for you, and you can use it, for example, debug application, right? Something happened in production. If you can get an archive from prod and just replay it in your IDE, put a breakpoint where things happen, and you can debug it. And it allows you to do things like replay merge. That is, you can replay from cold storage and archive, but still join the live channel. And it's very efficient because it uses the same disk format as the wire form, so it kind of uses Aeron framing from the transport to store data on disk and in just plain files. All right, that's all good. What else can you do with Aeron? Well, there is Aeron cluster. I don't know if you can see that well. It represents it. So what cluster is? So unlike Aeron transport and archive, this is basically just a library for you to send messages, and you decide if you want to store them or not. Cluster is concerned with building 24/7 reliable fault-tolerant applications. This is very popular now. Everybody's doing clusters, so it's kind of, instead of just being a cluster of a particular description of a product that you use, this gives you a vehicle to build your own cluster. So what you would do, you would run multiple copies of your application on multiple machines, and then Aeron will take care of, if machines go away, things will just continue. So you don't lose data. If you lose a leader or a follower, doesn't matter. Things will just recover and continue. And so underneath it, it uses consensus protocol. It's Raft-based, but unlike Raft by the book, it's not using, so it's non-blocking Raft. So there is no RPC part in it. So everything in Aeron is actually asynchronous. There is no blocking API. No blocking API, some in archive, but for convenience, not in the main message pass. So it has some interesting extensions because of that, to the Raft protocol, and took only 7 years to get it right. So it's very hard to build your consensus. And this thing gives it. So it basically gives you an abstraction called clustered service. You write your business logic within clustered service, and then Aeron takes care of everything else. You also have a cluster client. It's an API that you use to interact with. So being your gateways, your other clients that needs to talk to a cluster, you send messages into the cluster via ingress, and you get responses on the cluster via egress, so the outcomes of your service. And there are interesting restrictions. In order for this to work, your services have to be deterministic. That is, you cannot use things like random. You cannot read files from disk. You cannot even call system current time in your business logic, because the logic and the outcome of all the services, and actually the work that it's done, it has to be exactly the same, so that if you lose a service, you lose a node and that was a leader, the other node can continue where the other one was. And it does things like it ensures there is actually a consensus when you receive a message. It's not processed straight away. It's fan out to the followers, the consensus is reached, and only then the business logic is allowed to process it when the data was stored and confirmed by multiple parties. Very interesting piece. A lot of people like it. A lot of people use it for 24/7 critical applications. Comes with its own caveats. It's hard. It's not your enterprise Java. Like nothing in Aeron is enterprise Java. That's the biggest concern we've heard from people. That is like it's nothing like we've seen before. But that's what makes it special. So how special? Well, let's look at a simple test. Let's say I want to echo a message between two boxes, named here client and echo node. I'm sending a payload arbitrarily chosen to 288 bytes. Well, not very arbitrarily. It's 200 to 300 bytes is a common message size in finance. So we're sending this message over, and I want to receive it back. Well, if I just show you the numbers of Aeron, you don't know what the references point are. So let's start with a very famous in Java world messaging framework. I will not name it. I will only say it uses protobufs underneath. And what we can do with it, well, the only thing I managed to do with it, I managed to get 20,000 messages a second out of it. It started okay. If you look at P50, we're in a 360 microsecond world, but by P99, and that's basically the tail latency, that's what the Aeron concerns with, right? Nobody cares about P50s. If you don't know what I'm talking about, why percentiles are important, watch Gil Tanner talk, how not to measure latency. It's about 10-year-old by now. It's a brilliant talk, and he explained why you care about P99s, 3.9s, 4.9s, 5.9s, and why these events are not as rare as you might think. So, well, we started good, but essentially we ended up in, what, tens of milliseconds at the end of the day, and we did a minuscule 20,000 messages a second. Well, that's not brilliant. So let's look at Aeron. What can Aeron do? Well, we are sending just 1 million messages a second at basically 2-digit microsecond across. If we look at 4.9s, right there, we see there is like a couple hundred difference just there. But more importantly, we're sending 50 times more data. So you're looking tens of thousands of times better. And this is not maximum Aeron can do. Aeron can easily saturate 10 gig NIC. But that's not going to be a fair test, because at saturated NIC, you're going to have queues, you're going to have very bad latency. So in my tests, it was like 3.8 million messages a second, where the NIC just falls over. And if you run at about 3.6, you're running at 90-ish percentage of using a NIC, and it's very high probability you're going to get some bottlenecks. So another thing in like low latency world is that you never run your system saturated. You always need a slack in the system. I don't know if you've seen that before, but there is a famous hockey stick curve which shows basically relationship between load on the system and waiting times and queues forming. And at about 60 to 70%, the curve goes up, and then it shoots up exponentially. So the more you go to 80s and 90s, at some point you don't have any slack in the system. Everything just queued, and the time's there. By the way, if you practice Agile and you don't know that curve, you're doing it wrong. Because you typically run in your teams at 100% capacity. You say, okay, that person can do 4 tickets this week. Let's give them 4 tickets. No, he should be running 2 tickets or maybe 1. Why? Because things happen. Because somebody says prod just went down, and that person went for 3 days to debug production issue. All of a sudden, he can no longer deliver those things, but his pile is growing. So queues are forming. That's not good. The same here. So it would be pointless task to show you that Aeron can do 10 million messages a second when the network is dead. The point is, out of the box and default config, you get nice and flat latency curve, and you can shift lots of data. And you see, even at the max, it's still a microsecond world. Okay, let's step it up a notch. In Aeron, the media driver component is written in Java, but there is also one written in C. And when written in C, we can have things like kernel bypass. You can have those things in Java as well, with things like open and load and such. But in Aeron, we have an implementation specifically for solar flare NICs. It's called EFVI. It's the lowest level API that gives you 0 copy and stuff. At that level, you are building packets by hand. So you're literally creating Ethernet frame, IP frame, UDP frame, putting bytes on, do the big endian encoding, all that stuff. And we do that all in C, because the API is C. So if you're in that world, well, you want to single-digit microsecond performance now. By the way, this is a very old server. This is a Skylake from 2017. On a modern system, you basically can be around a microsecond, 1 to 2 mics on average with Aeron. Aeron has very little overhead. It's about a microsecond, we say, in UDP case. But you see, kind of, we stepped it up a notch. And again, if we look at 4.9s, well, it's 1,000 times faster just in this one. But if we take into account we're shifting 50 times more data, it's 50,000 times faster than very popular messaging framework. Let's step it up a notch. What if our participants are no longer in the network? You know, there is a lot of 10 years ago was a big push. Everybody copied Amazon, went web services, whatnot, all the multi-service architecture, and now people doing the opposite. They're building monolith back because they realized costs and maintenance burden and understanding debugability and all this stuff. We had it with Aeron as well. Some people would start with multi-machine distributed thing, and then they realized, well, it's much more efficient to buy a big server with like 140 cores and put 10 applications on it. In that world, you don't want to be send messages over UDP. Well, comes Aeron, and Aeron says, well, it's just a config change. Instead of Aeron : UDP, you say Aeron IPC, and all of a sudden, your things are talking again. No changes to your code, right? The best part of the Aeron IPC is that it's transparent. So you're sending messages, thinking you're sending messages, but you actually client and you have two client applications talking to each other in shared memory. If you're in that world, we're at nanosecond scale. You see, it's about 500 nanos for P50, and it stays in nanosecond pretty much up to 4 nines. And if, well, that's an unfair comparison. If we look at that, it would be like, so many thousands. I don't want to even multiply things, how much better that is. But that's not fair comparison because that's IPC versus network. So it's all good, and it's all messaging, and it's a toy example. Does it really matter? Well, I mentioned to you cluster, right? So cluster would be an example of fault-tolerant application where you bid your system or a national treasure of the whole Switzerland. 6 interbanking clearing in Switzerland, build an instant payment system, and it's a platform that is used, basically it's the fifth generations of their platform, and they had to roll out in this instant payment system for the entire country, but that system also handles all the payments between the banks. I don't remember the exact numbers. They gave a talk last year, was in hundreds of billions of dollars that the system is moving. So it's mission critical, and they've done it on cluster. So, well, if they've done it on cluster, can cluster do anything good? Let's compare pure messaging and pure IPC versus what the fault-tolerant cluster application can do. Well, it can still do 1 million messages a second. And that's a surprise, right? So not only it is at least 100 times faster at P4 than 20x messages on sending 2 messages between the machine. Not only that, it means that you received the message, you replicated it to 2 other nodes, you reached consensus, you did the business logic, and you did the reply. Basically, what, 5,000 times more efficient than just sending 288 bytes across 2 boxes if you pick up just a random library. That's where the power of this thing comes in. And you might not have a particularly low latency use case. For example, the 6 guys in Switzerland, they don't. I think their budget is 200 millis or something like that. But when they gave a talk, they said the most surprising thing for them was once they started using cluster is that they achieved their SLA without doing anything. The first deployment was already a success. And their usual experience is that you deploy a system and you spend half a year, maybe more, to tune it and do database query adjustments, whatnot, just to make sure that you could reach this SLA. And every time there is a new release, and just a little bit more data, it just breaks apart. And with Aeron cluster, it wasn't breaking. There is one thing worth mentioning here. I say Aeron cluster was DPDK. That's totally different environment, by the way. This is not running in the local network setup like all the other tests were done. It's running in the cloud. Well, in order to achieve 1 million messages in the cloud, you have to cheat a bit. So you need kernel bypass, and that's where DPDK is coming. That's a kit coming from Intel that basically allows you to talk to any network card through the same set of API. And cloud providers offer, so in their drivers like AWS, GCP, you can talk to their drivers through that, and that's what cluster uses underneath. If not for DPDK, we would not see 1 million messages a second here because of the fan-out case. Because if the cluster needs to send message to multiple parties and receive responses back, you have the traffic amplification. Because in the cloud, you don't have multicast. For every message you sent out, you have to duplicate it, right? So imagine you have an 1x, let's say 1 million messages coming in. You have to split it in 2, so it's 2 million messages out. And then you have to send 1 million messages back as a response. So that node is not doing 1 million transactions a second, messages a second. It's doing 3 million messages a second. And at that world, if you are doing it through normal BSD sockets, you can't do it. Because BSD sockets inherent user kernel switch, context switches, and just overhead of syscalls, you are looking at best case on the best machines, on the best tuned Linux system at around 1 million packets per second, so you can't achieve that. With DPDK, it's all done in user space, you're talking to the network card directly, you can achieve those numbers. With that, here's some references. Aeron can be found on GitHub. Agrona is the library that Aeron is using. By the way, everything in Aeron is built by us. There is no one, like we don't have, another unique part of Aeron, there is no dependencies. Because if you pull in dependency, you don't know if it's going to allocate, if you know it's going to start threads, you don't know what kind of tricks it's going to do. So Aeron is using only Agrona and SBE as a codec, but Aeron is codec agnostic. So if you want to use Aeron to send JSON files, be my guest, no problem there. You can choose codec yourself, but internally for archive and for cluster, Aeron is using SBE, is also built by the same people, Martin Todd, etc. Simple binary encoding, interesting format. If you're interested, have a look at that. The stupid parsing example is also here, and the two talks, one is Martin's talk about Aeron here, and the second one is Gil Tennis, how not to measure latency. So grab a photo of that before I move on to Q&A. Good. That was me. Adaptive is now stewardship around Aeron. It used to be just 4 folks looking and working independently. Now there's a bigger company behind it, but it changes nothing. Aeron's still open source, still there. If you're interested to learn more, 2 meetups are coming, one in New York, one in London. If you happen to be in one of the places, you can register, come talk to us, see what it can do. And we've done some case studies and shown performance on Aeron on cloud about 2 years ago now. And this will be updated soon. And I think that was it. And now it's time to do Q&A. I just need to do this. We all can see questions. I hope I can see them as well. I don't like the philosophic, I guess, to avoid allocations. Code my new object doesn't necessarily mean new allocation. Do you want to modify your statements, warnings? I don't. It's a good point. JIT can do magic. What if the method is not hot enough to be JITted? Or you are in a startup case, right? You just started your application. It's all cold. This will allocate until JIT kicks in, right? Until it's 10,000 iterations. JIT will do the compilation. It will take time. Then there will be replacement of your interpreted method with the JITted method, and so on. And that might repeat again. Plus, JIT will, for example, elide allocation if the object does not escape your method, right? You allocate the object like a pair or something, and you work on it in this method. That's all good. But if you pass it on to the helper method, it technically escapes. Therefore, hotspot doesn't do it. GraalVM will do it. So there are VM implementations there that are better in this regard, and certain languages like Scala love the GraalVM because they do a lot of those object allocations. Everything is an object. But if you care about latency, you don't want to allocate anything. If you want other examples outside of Java world, look at the work that Tiger Whittle is doing, and they wrote a financial database in Zig, and they allocate all of the memory statically at the start of the application. They basically just say, here's a chunk of memory, I don't know, 500 megs, and they work with it. Nothing within the application allocates anything. They just reuse the memory that was allocated for exactly the same reason. So it doesn't have to be Java specific, and hence I stand my ground by the no allocation. And I said, this is design principles for very specific use case. And that use case was low latency system with a particular set of requirements. If your requirements are different, be my guest, allocate objects. It's fine. As long as you can meet your SLAs, as long as your team members understand the code and everything is fine, absolutely fine. Those are just set of guidelines that guide this particular type of systems and that we care about. You care about other things. And it's fine to disagree. Would you recommend Aeron for normal Java applications without such aggressive latency requirements? Is it heavily geared towards HFT? It's not. Surprisingly, cluster is now being picked up by different use cases which are not HFT. I mentioned 6 where they picked it up. Their application is in 5th iteration. I think it's typical Spring everywhere, Tomcats, whatnot. And they chose cluster not because of the performance, but because of the fault tolerance. They had a requirement, hard requirement, 24/7 system cannot go down. And they chose cluster because of that. And they gave a big warning when they did the talk. They said, like, this is so hard. And if they would have a choice to do a normal 24/5 application, to shut it down over a weekend and do big migrations, they would do that rather than use something like cluster. But there is no specifics about HFT. In fact, if you want to use Aeron for like fast IPC, for example, that's also an interesting use case, because it can do interesting tricks up and slave to get fast IPC, for example, not zeroing out memory at any of the caller threads because conductor is in play. So don't use threads and then everything in Aeron is asynchronous. Yes, it's asynchronous without threads. How cool is that, right? So what I mean by asynchronous in Aeron, it doesn't mean completable future style, fire off, do this, and I'm going to sit and wait. No, it's I'm trying to offer a message to Aeron, and Aeron tells me back pressure. It means I'm a publisher, I am overflowing or overloading the subscriber, and it cannot process message. And here I have choices, right? Instead of me being blocked and waiting for that message to go through, I have a choice. I'm given a choice back, and it's like, okay, do I propagate back pressure, for example, to the calling service? Maybe the user UI, saying to the user 503, service unavailable. Or do I spin for a bit, try hard, and then give up? Or I have choices. If you have a blocking API, you don't have those choices. So Aeron basically gives you that. Underneath, as I said, in Aeron, things are in separate threads. For example, sender, receiver, and conductor. And they work as state machines. So it's basically while true loop on every of those, and they do the same logic over and over again. Like sender will say, okay, do I have any publishers? Yes. For every publisher, pick a packet, send on the network. No packet, no nothing. Keep on going things. And like, if there is nothing to do for it, it will just spin. Agrona has things called idle strategies, which you can pick up and use, for example, if you don't want to burn CPUs and stuff like that. So it's different Java. When I joined the project in 2019 with all my enterprise Java background, it took quite a bit of adjustment to get used to this style of code. But once you're in, you don't want to go back. It's like you feel dirty every time you look at somebody's like, oh, it's log4j statements every other line. How brilliant it is. I don't even want to profile this because it's going to be 95%. It's like, you know, you run the profile and then say like, okay, trick, where is the business logic? And it's like, if it's 2% of CPU time, you're great. Everything else is your frameworks, your logging, all that. And this is so boring in a way because it's like so predictable. This is different. And it gets time to use to. Which are the bad binary protocols? I don't want to say anything bad about protobufs, but I said protobufs. No comments. All right, I think we're out of time. I have to stop. Thank you very much for coming. It was a pleasure seeing you.